Hello, everyone. My name is Nicolae Tusinschi. I'm working at OneSpin as a product specialist for design verification, so basically working on many interesting stuff where, yes, RISC-V is one of them. And what I am actually going to talk about today is verification of RISC-V SoCs by formal means. But first of all, I would like to talk a bit about who are we, who OneSpin and what we are doing. So we at OneSpin, we provide verification solutions that target most of the phases in the verification flow from design, integration, and implementation for SoC, ASIC, FPGA verification flows. And the golden target is to assure IC integrity. So in more details, so we focus on the functional correctness area, where also we focus on the safety, especially for automotive and industrial. And one new area that we focus on is trust and security. So all of this, especially trust and security and functional correctness, we apply to the RISC-V as well. So coming back to RISC-V, so we know that verification, and we heard a lot during the summit that there is a concern, and RISC-V has a lot of verification challenges. So what we do, what are the challenges? So one thing that we need to make sure is, does the register transfer level, the RTL, precisely implement the RISC-V instruction set specification? And as RISC-V is becoming very popular, so there is also, well, we have already like around 80 open cores. Some of them went to silicon. But verification of these cores is very hard, and this is due to the fact that there are complex microarchitecture, and because RISC-V has this allows you to plug in extensions. There are many configurations, and from the formal world, what we have so far is basically it's difficult to set up, and also the results that we get are bounded. And when you have bounded formal proofs, the bugs and additional logic remains undetected. So what we did, so talking about the methodology, so the RISC-V Formal Methodology, so we have a specification, which comes in forms of a PDF. So in example, this is the opcode of the load word. There is a detailed explanation in the specification of what this instruction should do. So basically what it does, the specification defines some architecture registers, like register file, like program counter, control status register, and others. Also, it may define some values. And execution of this instruction or the exception, the specification defines some update of this architecture, registers, and memory request. So it looks pretty simple, so basically. And what we did, we formalized the instruction set architecture. So we capture the effect of the instructions on architecture state. We capture the effect of instructions on output to data memory, and we formalized all of this in the system Verilog assertion language. And of course, we targeted not only the base instruction set, we formalized all the rectified extensions. In the end, it looks something like this, not very fancy. So the opcode, of course, we decode which type of instruction it is. What are the fields? Is it a memory instruction, etc. Now, when we have formalized the instruction set architecture, the problem comes that in formal, the tool generates all possible combinations. And because and here comes in play the microarchitecture details. And these microarchitecture details are implementation dependent. Like the pipeline length can be different, and also there is single issue, multi-issue, in-order, out-of-order implementations, and these are playing a big role in the verification. And what we used, we used the so-called interval property checking methodology. So basically what this interval property checking methodology does, it links link the pipeline to sequential execution of instruction. So you basically capture the full effect of one instruction or exception in the pipeline. And the meaning of this is that basically the instruction is captured standalone, and it does not start from reset, but from a generic valid state. So you will see in the next slides how does this look like. And the interval, basically there is a limited number of cycles to reach the generic valid state. So basically this limited number of cycles is the cycles until the instruction leaves the decode stage and until it is retired. To make it more easy and to adapt to different cores, basically the interval property methodology is decoupling the instruction set architecture, the standard, from the microarchitecture details. So with this methodology, with a formalized specification, we ended up in having properties. Properties that can be formally verified. And as you can see in this code snippet of the load word instruction, basically there is a series of sequences, some conditions. So basically we use in the property the ISA formalization. We also introduce the microarchitecture details, like of course, when an instruction is ready to execute, there is no stalling, there is no exceptions coming from fetch, and also the Dcache protocol delivering read data as a result. And this needs to prove that, okay, next cycle, there is another instruction ready to execute, and also check the expected register file and the Dcache request from ISA. Does it look similar? Yes, it's system verilog assertion language. And it's quite familiar for verification engineers to apply it. So putting all together is what we have done so far is we formalized the instruction set architecture, and the input to the tool is the implementation itself. And because these microarchitecture details are core dependent, the solution is semi-automated. So basically you specify what is your configuration of the core, and the tool generates a set of assertions according to your configuration. Then you can take these your assertions and you introduce your microarchitecture details, and then you can run the formal proofs on them. In order to help the user to speed up, we enabled some functionality to extract some microarchitecture details directly from the RTL. Let's say you have the rocket core, and you know that, of course, the assertions need to be, comes into a checker. They need to be bound to the core. The rocket checker is, when it generates the code, it generates use random naming. And basically, in order to do this binding, you would need to find out what are the register names. And this is also easily to extract from the RTL. Also with some other microarchitecture details. So this comes in a form of verification app and completely verifies the RISC-V core RTL implementations with full proofs. So we get unbounded proofs on the properties. So it takes less than a week to set it up. Basically, when I say the week to set it up is the week when you need to adapt your properties with your microarchitecture details. And it's proven on 32-bit, 64-bit commercial and open source implementation. I will show next the results that we have achieved with this methodology. So verification results, this is the Rocket Core example. So I list here a selection of issues we have found. So basically, Some of them are, one is really interesting is because when we apply the methodology, we spotted immediately that the seize instruction is not in the specification. And yesterday, we found out that the seize instruction will be introduced will be inserted in the specification. Yeah, also there is a couple of bugs, the selection of bugs that we reported in the GitHub, so you can check it there. So some of them are confirmed, and some of them are still under investigation. And all of these bugs are identified with this methodology. So we don't stop at the Rocket core. For Rocket core, we checked and validated the methodology for different configurations. We went further, and we applied it to the RISC-V. So basically, RISC-V is a 32-bit implementation from University of Zurich and the University of Bologna. And applying this methodology, we have identified several issues. So basically, there are so many that we classify them into the exception handling violation. So we classify them in some classes, like exception handling violation, exception raising violation, some floating point extension violation, some trap returning handling violation. These are reported in the GitHub. You can go and check them out. But basically, the bugs that are identified are not trivial bugs. So basically, the bugs are related to some corner cases that the core is exercising. And like something illegal instruction, raising violations, etc. So there is a series of interesting results that we have found in RISC-V core. And this helps us to validate the formalization we have done with two different industrial design already. So the RISC-V with the Core 5 now, and the Rocket. For Rocket, we have applied it to 32-bit, 64-bit, all user modes. Unfortunately, for RISC-V has a custom debug support, so the debug has been verified only for Rocket. But moving further, so okay, you have the core, but the core itself is not standalone, so you have to plug it. And going beyond of it, the SoC verification where this core is integrated, we leverage the formal automated apps. And by this, I mean, so there is a portfolio of formal automated apps that we have in OneSpin, and we selected the areas where this can be applied, and we applied it to the Pulpino. Coming to Pulpino is an open source project started at Zurich and Bologna. It's built for two open source cores, the RISC-V and Zero RISC-V. Has a rich set of peripherals. You can see also that it has the Bamba buses, the AMBA buses. UART, I2C, yeah, it's an area where you can play. And applying all of these automated apps, we have also identified bugs. And we have identified issues in the APB interfaces. Some of them are low-hanging fruits coming directly from the automated code inspection. The floating point addition delivers an incorrect results. And recently, they have completely modified the FPU to a new implementation. So yeah, what we have applied the protocol compliance. So we have verification IPs for AMBA. We have applied the protocol compliance for I2C, a full range of automated RTL checks, FSM reachability analysis, dead code analysis, interconnect verification, and of course there is more space to apply into the SoC level. So yeah, summarizing, I'll bring this back. So we have validated a verification solution for RISC-V core that takes less than a week to set up and runs only 2 hours on a complete core. It's proven on 32-bit and 64-bit implementations. During the setup, we work together to accelerate it and to run verification as soon as possible. And what I want to say is that the RISC-V cores and the SoCs can be exhaustively verified by formal means. So it's well suited to detect all undocumented instructions, side effects of instructions, and instruction sequences, reaching the unbounded proofs, verification beyond ISA compliance. So it's not only talking about the ISA compliance, but takes into account the microarchitecture details. We are not yet there at the supporting the custom extensions, but we are working into that direction to automate it and to make it more easy to deploy. As I said, this has been applied to multiple RISC-V designs and configurations, and we have a selection of issues that we have identified and reported to the GitHub repositories. On this note, I would like to thank you, and if you have any questions, just feel free to ask. So we support everything that is ratified. The base instruction, compressed, M, F, D, A. But once they are ratified, we're going to need to add them as well. So for us, an instruction is basically you specify the trigger of the instruction. And you specify it by giving what is, for us, is the property starts when the instruction is leaving the decode stage. And we capture the full effect until the instruction is retired. So basically, we also prove that in the next cycle, the next instruction is leaving the decode stage. And this is the generic valid state that I was talking about when I was presenting. So the focus here is we have the decouple, the decaches, and you need some constraints on the interface. And the methodology that we use is the assume guarantee. So basically, we verify them that these assumptions, we verify them on the decache, and then we assume them. And this way, we make sure that we don't over-constrain or something like that.